Uniform random variables, section 5.2. Uniform random variables are examples of continuous random variables that can take on any value on the given interval, not just whole numbers. The main continuous random variable that we'll be working with is the bell curve, or the normal random variable. But the uniform random variable has a lot of the same properties as the bell curve, or any continuous random variable has a lot of the similar properties. The probability of a uniform random variable on a specified interval is equal to the length of the specified interval divided by the length of the entire interval. Example would be commuter trains arriving every 16 minutes. The wait time for the passengers after entering the platform will be somewhere between 0 and 16 minutes. And we can let x be a random variable representing the length of time a randomly chosen passenger must wait. So that would be a uniform random variable. We want to sketch the graph, find the probability that the passenger must wait less than 2 minutes. So in symbol is the probability x is less than 2. So the wait time could go anywhere from 0 to 16, so the probability, it's not exactly a probability function, but it's a probability density function, is 1 divided by the length of the interval. So it's 1 divided by 16. So our probability density function goes like this. To get the probability, we want the width of the given interval divided by the width of the entire interval. So the given interval is, or the specified interval is from 0 to 2. So its interval width is 2 minus 0, which is 2. And the entire interval goes from 0 to 16 minutes. 16 minus 0 is 16. So 2 divided by 16 is 0.125. So the probability that somebody waits less than 2 minutes would be 0.125. And this actually corresponds to the size of the shaded area on this graph. So if this is a rectangle, if you look at the area of this graph, the area is the length times the width, and so the height, in this case the height times the width. So the width is 2, the height is 1/16. So 2 times 1/16 is 2/16, which is a decimal 0.125. So this is actually a property of any continuous random variable. We don't have a probability function, we have a probability density function, and the probabilities are actually over intervals, and it corresponds to the size of the shaded area. Part B, probability a person waits more than 13 minutes. So the graph goes from, the shaded area goes from 13 to 16. So let's make the density function, I guess, 1/16. So it's the specified interval, which is 16 minus 13, which is 3, divided by the entire interval. 16 minus 0 is 16. 3 divided by 16 is 0.1875. Between 7 and 12 minutes. So the specified interval goes from 7 to 12. So 12 minus 7 is 5. And the entire interval is 16. 5 divided by 16.3125. Exactly 8 minutes. So this is kind of a degenerate case here. We don't really have any width here. We're going from 8 to 8. 8 minus 8 is 0. 0 divided by 16 is 0. So the probability of waiting exactly 8 minutes would be 0. And in fact, the probability of that x is equal to any specific number is equal to 0. And that's a property for any continuous random variable. because the variable takes on an infinite number of possible values, the probability of any given value is going to be 0. In order to have a positive probability, you have to have an interval. So if we want, and also the size of the shaded area is also going to be 0 if we do length times width. Well, the width is 0, the length is 1/16, so the area is also 0. If we do, on the other hand, if we instead of doing exactly 8 minutes, if we say what is the probability of approximately 8 minutes rounded to the nearest minute, so that could be anywhere from x could be anywhere from 7.5 to 8.5. So then, so now we have an interval here, not just a single point, and it goes from 7.5 to 8.5. So the interval width is 8.5 minus 7.5, which is 1. 1 divided by 16.0625. So so if we express it in terms of approximately 8 minutes, then we do have a positive probability. What is the probability the person waits between 0 and 16 minutes? So that's going to be the entire interval. 16 minus 0 is 16. 16 divided by 16 is 1. So, and that's also a feature of continuous random variables, that the probability that the entire shaded area is corresponds to probability 1, and the entire shaded area is equal to 1. So it's certain that if the trains are running every 16 minutes, then it's certain that the waiting time will be somewhere between 0 and 16 minutes. We can also find the 5-number summary and make a box plot. So the first quartile so is going to be 25% of 16. We could set up an equation for this. If we do x minus 0 divided by 16 minus 0 is equal to 25%, or as a decimal point 25. So that means that x minus 0 is just x. X over 16 is equal to 0.25. And if you multiply both sides by 16, we get x is equal to 0.25 times 16, which is equal to 4. So so that'd be 4 minutes. So the first quartile of Q1 would be 4 minutes. And the second quartile, x minus 0 divided by 16 minus 0 is equal to 0.5. Second quartile is also called the median. It's also the 50th percentile. So that means that x over 16 is equal to 0.5. And if we solve for x is 16 times 0.5, which is equal to 8 minutes. And then the third quartile, x minus 0 over 16 minus 0 is equal to 0.75. Third quartile is the 75th percentile. That means that x over 16 is 0.75. That means that x is equal to 0.75 times 16, which is equal to 12 minutes. Okay, so to summarize here, we have, well, the minimum would be 0 minutes. First quartile 4, second quartile 8, third quartile 12. The maximum waiting time, if the train's running every 16 minutes, would be 16 minutes. So the box goes from Q1 to Q3. So it goes from 4 to 12. Line inside the box is for the median, which is 8. And the whiskers go out to the min and the max. So this is a perfectly symmetric plot. That's a feature of uniform random variables. They're symmetric, completely symmetric, and the mean is same. The mean is going to be the same as the median, and it can be shown with using calculus that the variance is L squared over 12. I'm not going to really emphasize that, but that's the in this case it would be the length of the interval is 16 squared divided by 12. 256 divided by 12. 21.3 repeating threes, and then so S squared or sigma squared rather, variance. And then if we take the square root of that, we get the standard deviation sigma 4.618802.154, and we can use the notation x distributed uniform. That's u parentheses 0, 16. So it's uniformly distributed on the interval from 0 to 16. So for the binomial, we use a b. For Poisson, we can use a p, just to indicate which of the special random variables we're looking at. And that concludes this presentation.